Hello, my name is Madeline Endres, a PhD student at the University of Michigan, and today I'm going to present our paper relating reading, visualization, and coding for new programmers, a neuroimaging study. Now, the title's a bit complicated at first glance, but at a high level, our work uses brain-based imaging to understand what's really going on in novices' heads when they program. Specifically, we investigate if programming for novices is more like reading or if it's more like visualizing shapes, two general cognitive processes that have both been connected to programming in previous studies with expert developers. So first, let's talk a little bit about why I think this work is pretty cool. In general, understanding the cognitive basis for software engineering is important because it can help us understand the cause of observed effects and from this, implement more effective policies and tools. Neuroimaging is a particularly appealing way to study this because, unlike subjective self-reporting, it allows us to objectively measure cognitive activity. Now, several recent neuroimaging studies have helped gain insight into programming. These studies are definitely exciting, and the authors propose that their work could influence many areas of software engineering, including pedagogy, technology transfer, and adult retraining. However, much of this work has been exploratory. Today, we're going to get one step closer to making neuroimaging results actionable through our study of novices and its concrete implications for pedagogy and expertise. Now, in neuroimaging, when you want to understand the cognitive basis of a new task such as programming, you generally compare it to a different, better understood task in something called a contrast-based experiment. The two most common tasks that have been previously compared to programming are spatial reasoning, which can be thought of as the ability to mentally manipulate 3D objects, and reading. One such neuroimaging study by Floyd et al. Used a contrast-based experiment to find with increased programming expertise, programming was actually less distinguishable from reading in the brain. This is intriguing because understanding the cognitive basis of programming expertise could lead to concrete ideas on how to help novices become experts faster. Unfortunately, however, the Floyd study only included developers or students who had already had several years of programming experience, and the observed connection with expertise was exploratory. In fact, all previous software engineering neuroimaging studies have exclusively imaged programmers with years of experience or schooling. In this paper, we help fill this gap through the first neuroimaging study of novice programmers conducting code comprehension. We focus on two main questions. First, we want to understand the cognitive basis of code comprehension for novices. Now, this is a broad question, so to tackle it, we focus on comparing novices' brain activation patterns while coding to those while completing spatial visualization and language-based tasks. We choose these two cognitive tasks because they have been used in previous expert-focused studies. For our second research question, we directly investigate the potentiality for neuroimaging to inform pedagogy through seeing if brain activation patterns captured at the beginning of CS1 can actually predict future programming ability. To answer these questions, we use functional near-infrared spectroscopy, or FNIRS, to capture the brain activity of novice programmers in their first semester of university programming. FNIRS uses light transmitters and receivers in a special cap to measure the brain's blood oxygen levels, and it supports studying the brain while programming in a natural environment. With our high-level plan in mind, let's now move on to experimental design and data collection. To study how new programmers understand code, we recruited our participants from the same Michigan introductory programming class during the third week of the semester, and we conducted brain scans in weeks 4 through 6. Conducting scans at this early point allowed us to study novices who had encountered basic programming syntax but had yet to have much experience actually programming. We also followed up with participants at the end of the semester with a programming test. This test helped us answer our second research question: can brain activation patterns predict future programming ability? With this timeline in mind, let's look at the brain scans themselves in more detail. During the scans, we compared brain activity while participants completed 3 different tasks. For the programming task, we showed participants problems based on topics covered in Michigan's CS1. For spatial visualization, we used mental rotation tasks that are a standard proxy for spatial reasoning. And finally, for reading, we used GRE-style fill-in-the-blank questions. Each participant's scan session, including the setup, lasted 2 hours. As a visual of the study environment, here's my excellent undergraduate researcher, Annie, wearing an FNIRS cap during a pilot scan. All participants were shown 90 stimuli, 30 of each type. We had 31 valid participants, 24 of whom were female. To analyze the data, we used best practices from the psychology literature to compare task-based activation by brain area. Now that we've covered our design and data collection, it's time for the exciting bit, the results. As a quick reminder of our research questions, our first question really gets at the cognitive basis of programming, asking if novices rely more on spatial visualization or language brain areas while programming. Our second question, on the other hand, asks if we can use brain activation patterns to predict future programming ability. So for our first question, do novices rely more on spatial or language areas while programming? We found that the answer is that novices rely more on spatial areas rather than language areas. Specifically, we find more substantial differences between coding and reading than between coding and mental rotation. To help visualize this finding, here are some color-coded heat maps that highlight relevant brain regions with coding versus reading on the left and coding versus mental rotation on the right. Unfortunately, time constraints preclude a thorough discussion of how to read these figures. Some of you may have seen this type of graphic before, but if you haven't, I encourage you to ask me about them after the presentation when I can go through them in more detail. In general, however, more colored dots mean that there are more significant differences, and there are more colored dots in the left picture between coding and reading than in the right picture between coding and mental rotation. This difference in dots is particularly apparent in the right hemisphere and in the frontal cortex. Now, even though programming for novices seems more similar to spatial visualization than to reading, we do find that coding is distinct from both of them. In particular, we find that for novices, coding is cognitively demanding as we see stronger working memory activation than for either other task. Okay, so we found that for novices, programming looks more like spatial visualization than like reading. Great, but why do we care? Our results help answer this question by providing support for changes in pedagogical practice. In contrast with previous studies with experts, we find less cognitive similarity between reading and programming. This finding has implications for developer training and pedagogy. At the bottom of the slide, I have briefly outlined one way our findings could influence practice. In learning theory, spatial reasoning is sometimes viewed as a general problem-solving toolbox. Thus, the observed convergence of programming and reading through expertise may be caused by programmers learning domain-specific strategies that use more reading-associated cognitive processes. If this is true, directly training reading-based domain-specific strategies may help novices become experts faster. In other fields, people have used similar neuroimaging results to influence training in this way. So to summarize research question 1, we found that for novices, spatial reasoning is more similar to programming than reading at a cognitive level. This is in contrast to results with expert developers and has implications for future programming, training, or interventions. Moving on to research question 2, can brain activation patterns captured at the start of CS1 predict future programming ability? To answer this question, we conduct an exploratory study where we correlate brain activity interactions on the 3 tasks with scores on the programming post-test. Doing so, we find that, yes, it is possible to use brain scans to predict performance. Specifically, we find that less similar patterns of activation for coding and mental rotation in the right frontal hemisphere at the start of the semester predict better outcomes on the end of semester programming assessment. This analysis is exploratory, so we can't yet say why less similar patterns of activation for coding and mental rotation predict better performance. One possibility that aligns with the implications discussed in research question 1 is that novices who transition earlier away from general spatial skills to reading-associated domain-specific strategies ultimately actually make more progress. This result, therefore, provides impetus for earlier pedagogical interventions in computer science. Finally, on a bit of a separate note, I want to be clear that we do not see our results as supporting essentialist-based theories of programming ability. Rather, we think they provide insight for more effectively understanding and removing computing barriers. However, if you want to talk more about the ethical considerations behind using medical imaging to predict performance, definitely ask me during the discussion. So in summary, for research question 2, we found that, yes, novice brain activity when programming can predict future programming ability. This finding provides another window into understanding and ameliorating computing barriers. In conclusion, in this paper we conducted a study of 31 novice programmers where we found that programming is a challenging working memory-intensive task. We also found that spatial reasoning is more similar to programming than reading for novices, and that programming brain activity can predict future programming ability weeks later. Our results have implications for bettering the training of future programmers and software engineers, and our materials and replication package are available on the link in the box. Thank you for attending, and I look forward to your questions.